Welcome to the CDL Evolving Energy webinar series. My name is Florence van der Tuin and I'm the office manager at CDL. I also support client relations and help drive business opportunities. It is my utmost pleasure to welcome you and open today's webinar. Today focuses on the exciting and timely topic, the release of the Geological Carbon Storage Atlas of Eastern Canada. As Canada advances its carbon management strategy, carbon capture, transportation, and permanent geological storage of CO2 will play a critical role in achieving long-term climate objectives. In part one of this webinar series, we will share the project results and explore the subsurface factors involved in geological carbon capture storage, including basis analysis and storage potential highlighted in the atlas. Before we begin, I'd like to go over a few housekeeping items. Today's presentation is being recorded and all attendees have been muted. We will have a Q&A session in the end of the webinar, so please feel free to type your questions in the Q&A panel or the chat throughout the presentation, and we will address them afterward. CDL has been actively involved in the energy initiatives spanning oil and gas exploration, development, CCUS, critical minerals, geothermal, and emerging energy opportunities across North America. We are excited to continue expanding these conversations through future webinars and technical releases. With that, it's my pleasure to introduce you to today's presenters, Christa Williams and John Cody. Christa Williams is a seasoned geologist with over 18 years of experience in subsurface exploration, development geology, and commercial growth. She currently serves as Vice President of Business Development at Canadian Discovery, with a focus on clean energy and carbon capture and storage. Christa brings a strong combination of technical experience, commercial leadership, and deep commitment to the geoscience community. Joining her today is John Cody, who brings 35 years of experience across oil, gas, and environmental industries. John has an extensive background in basin scale, exploration, prospect evaluation, petroleum systems, and reservoir characterization, with experience in Western Canada, East Coast Canada, Ecuador, and North Atlantic. He is widely recognized for his technical leadership and global exploration expertise. We're very much looking forward to today's presentation. And with that, I will now hand it over to Christa and John to get us started.
Wonderful. Thank you, Florence, for the great introduction. So we are very excited to discuss this project. We've been working on this for over a year and a half now. And we are going to tell you today and talk to you about the results of the CCS potential in Atlantic Canada as well as Quebec. I will be co-presenting with my colleague, John Cody. This presentation is going to get into the geological details and complexities of storage results of the project itself. That's part of why we have broken out releasing this into two parts, so that today can be more of a geo focus, and then part two, which will be next week on May 5th, will be more on the economics and transportation costs that could be associated with a project developer looking in this region. So in terms of agenda, we're going to talk about the project proponents. We're going to talk about the scope of the atlas, why the atlas was needed, what our methodology and results were, and then we're going to go into more details with an example evaluation through the Scotian Basin itself. We're going to talk about the overall conclusions, and then stay tuned for part two, which is CO2 storage and full CCS value chain cost modelings next week, May 5th. So this work was undertaken with partial funding support from Natural Resources Canada, with additional support from carbon removal developer Deep Sky, as well as in collaboration with NRCan CanmetENERGY. So it really does take a village in a lot of senses to get these projects up and off the ground, but it is really foundational in terms of helping understand the potential of the resource abilities within this region. So why was the atlas needed? The atlas was needed because high quality data sets and maps are really going to help project developers fast track their CCS strategies and focus their investments into the most favorable and highest quality storage reservoirs. This information provides key information to enable industry, government, Indigenous groups, communities, and others to make informed decisions. So CO2 emitters, storage project developers, public regulators, governments, investment community. And really what this does in a lot of ways is it helps to demystify the sequestration advantage and enable informed investment decisions based on project area, quality, and risk. So here's our study area. Our study area is relatively large. So it spans 5 different provinces. We have Quebec, New Brunswick, Nova Scotia, PEI, and Newfoundland and Labrador. On the right, you'll see a map that shows our screening based on the data and availability where we were able to focus our efforts. So initially, we started with 38 basins across Quebec and Atlantic Canada, and then they needed to be evaluated based on data quality and availability. So the screening criteria focuses on viable reservoir seal pairs in deep saline aquifers or depleted hydrocarbon pools. And it also excludes overpressured and shallow, less than 800-meter formations where CO2 is not seen to be in that supercritical state. Now, this is a function of depth and temperature, but we're going to talk more about that as we step through the presentation. The basins that are outlined in green tell us that we have sufficient data. We have sufficient wells, seismic, and subsurface data. So within these selected basins, our storage complexes are further screened to identify what the viable reservoir seal pairs are. Next, you'll note that we have yellow basins. These yellow basins have partial but incomplete data. And so we treat them as qualitative basins themselves. So we did do an assessment, but we weren't able to do the full characterization assessment that we were able to do on the green basins. Next, you'll see a number of basins that are outlined in red. This is where we had insufficient data. So these basins lacked meaningful well and seismic control and were excluded from the evaluation entirely. In some cases, there were geographical constraints such as Iceberg Alley, as well as the proximity and distance to onshore emitters. So next, what types of geological storage did we look at? For the purpose of this study, we're really only focusing on depleted oil and gas reservoirs, which are type 1, delineated in the diagram, and the unused saline aquifers, which are high salt concentration type 3, delineated on the diagram itself. These aquifers are deemed unusable for human consumption or irrigation. You can also see there are many other forms of geological storage, but for the scope of this study, we are solely focusing on the depleted pools as well as the deep saline aquifers. So as mentioned, this is a very large study that goes through the full scale analysis of identifying the sinks, the sources, and then all of the connecting pieces that come together. Today, we're just going to talk about 1 and 2. That's going to be the regional screening of the basins, and then understanding the complexities of the geology, mapping out the storage complexes, the net reservoir thickness, permeability, volumetric storage, and containment. As alluded to, next week, we're going to be talking about CCS workflows and data sets, as well as tying this to the national CCUS assessment framework that CanmetENERGY has been working hard on. So now we'll talk about the study methodology. So how do we choose the right place to store CO2? Now, next, what I'm going to do here is I'm going to start relatively general, and then we're going to get into a lot more of the complexities that will increase throughout the presentation. So bear with me. I want to make sure that we're all starting from the same framework in terms of what it is that we need to assess from a geological parameter. So first, we need to find the right rocks. We need to find the reservoir and seals. We need to look for the rocks that can hold the CO2 and rocks that can seal it in like a lid so it doesn't leak back out. Next, we need to estimate the thickness and porosity, the space inside. So rocks that are more sponge-like or have a higher porosity can hold more CO2. Then we need to understand the environment. We need to understand the pressure, temperature, CO2 density. How packed or dense the CO2 is going to help us know how much can actually be stored in the rock. Then we need to map the shape of the subsurface layers, the geological structure. We know that CO2 and fluids can move through cracks or slope upwards, so we need to know the layout and make sure that it stays put. Then we need to see how well the rock is going to accept the CO2. This is the injectivity. This tells us how easily CO2 can flow in and fill the storage space. Then we have to take all of that information, wrap it up together, and understand the hydrodynamics. So we've got water already underneath the ground, and it affects where the CO2 can go and how far it might move. The schematic on the right shows a deep cross-section block of the Earth with drinking water that we can see shown here at the top, layers of rock that can trap the CO2, and a number of seals that are going to be between them that are going to stop it from rising. So this helps us really understand how to make safe long-term plans for storing CO2 underneath the ground. So as we're going through our assessment, we need to address and ask the right questions. Does this formation have the right kind of rock and seal for safe storage? Is there enough space to store a meaningful amount of CO2? Do we already have good maps and data to help estimate how much CO2 it could hold? And if not, what extra mapping and analysis do we need to fill the gaps? So on the right, we have an idealized stratigraphic column showing lithologies, formations, ultimately the reservoir seal pairs. So this is part of a storage complex that we're going to be taking a much deeper dive into. But the reality is that we're going to have many different lithologies and formations, and each basin is going to have its own unique characteristics that need to be assessed and addressed accurately to characterize the geology for storage. The subsurface data set is compiled from publicly available sources that include academic studies, technical publications, consultant reports, and government data sets. And our key inputs include well header information, well reports, formation tops, logging and downhole testing, and core measurements. So now that we've gone through, we've set the stage, we know we need to know the pore space, the area, the thickness. Now we need to start to take that apart on a storage complex basis, but also taking that all out into a basin characterization. So we have to go from those known points to those unknown points and grid that out for each map so that we can put all of these parameters ultimately into the formulas that are going to help us understand and calculate what the storage potential is. So this is an example from the Magdalene Basin where we have 3 different storage complexes. So we've got the Cable Head, the Green Gables, and the Burdell Formation. And this is illustrative to show that we've got porosity maps that have been made for each one of them and then gridded out, as well as temperature maps and pressure maps. Now there's going to be slight variations between all of them, and then it's a matter of understanding the geometry of those units, how they're connected laterally as well as vertically, and any sort of heterogeneities that we can see there to understand ultimately what we're going to be able to do with that data and how good that storage resource is going to be. So you've heard me reference critical CO2. So critical CO2 is not a gas, it's not a liquid, it's somewhere in the middle. It's a bit of an emulsion. But the important piece here is that it really depends on the depth and the temperature. So deeper and higher pressure, you're going to get denser CO2, which means that you're going to be able to store more in less space. So if you look at the schematic here where we've got CO2 in a gaseous state above the surface, and then we look as we get deeper and we compress it further, we'll be able to have a smaller molecule that we can store more of. So ultimately, we need all of these parameters to help us understand what the storage potential is. I have to give a shout out to my colleague at Entropy, David Hills, who provided the schematic for this. But it's a nice way for us to step through the different components that we need to look at. So we need to first off understand the area, how wide the reservoir is, the thickness, how deep the usable part of the formation is. And then we need to step through to the porosity. How much of the rock is empty space? CO2 density depends on the depth, pressure, and temperature. And then we need to talk about the storage efficiency. So how much of the pore space can actually be filled with CO2? So the storage efficiency, also commonly known as the E-saline coefficient, helps us understand that not all the pore space can be filled with CO2. Some space stays filled with water or can't be reached. So the storage efficiency tells us how much of the pore space we can theoretically use. It also helps us account for unknowns or variations that cannot be determined because the data set that is available. The range of values used for the storage efficiency factor reflect the uncertainty and variability in the data, but they're also quite representative of these large-scale regional assessments. You're also going to see this related to our full cycle as we step through the example further in the presentation. So now we're going to talk about the results. So quantitative results. So these are for the 7 basins that we're able to categorize green. If you remember back to that original map where we showed those green basins. So we've gone through, and you'll note that we have used a traffic light system. So the traffic light system, as described earlier, we've got green, which is favorable, yellow, which is uncertain, requires further evaluation, and red, which is higher risk or unsuitable at this point in time. So storage targets were delineated only within geologically viable areas where suitable reservoir and seal conditions are present. The prospective CO2 resource was calculated using reservoir parameters such as depth, thickness, net to gross, porosity, pressure, temperature. This is all derived from literature or published reports or from the raw well data within the specific areas. So the key findings is that there is significant, the key findings are that there are significant variability in the storage potential, reservoir quality, and seal integrity as you step across this large, vast geographical area. Opportunities range from, in some cases, we're going to see large-scale hub developments, meaning that you have high potential, or smaller localized projects that are going to target specific emitters. We have stack potential in some basins that contain multiple storage complexes. And that's what our P50 estimates are going to include, is that stacked resource assessment where you have multiple complexes that are present within the basin itself. The Scotian Basin is a good example. Again, we're going to take a deeper look into this where we've got 4 different storage complexes, which help equate to some of the larger storage potential that we see within that basin itself. And the other point to note here for model considerations are these are regional models. So they provide average estimates of porosity and permeability. And there are going to be areas that you have local heterogeneities that remain important. So site-specific data is crucial. And as you're looking for any of these areas for further development, you need to always go to the next step of your characterization. So here's a map of those 7 quantitative basins. One of the things to note is we've got onshore and offshore basins. Onshore is more accessible. Offshore has higher storage potential, but different challenges from transportation and economics. So our offshore basins are the Scotian, South Whale, and Jeanne d'Arc. They stand out with thick, high-quality stacked aquifers. And our onshore basins are the St. Lawrence Lowlands, Moncton, Windsor, and they offer smaller scale opportunities that are going to be tied to local emitters. You can also see that we range anywhere from 0.02 up to 4 to 4.9 megatons per kilometer squared. So these models are effective, again, for regional scale predictions, but represent average conditions. They may miss that local heterogeneity, and even the lower ranked zones that are showing up as yellow or red could have higher porosity and permeability pockets that exist. So they should be really verified with observed data or collecting new data. Some of these basins offer stacked storage potential with multiple reservoir seal layers at different depths that enable CO2 storage in separate vertical formations. Offshore basins like the Scotian, South Whale, and Jeanne d'Arc are notable, again, for their thick, high-quality aquifers. And then the onshore basins have a lower overall potential, but still may support smaller localized CO2 storage projects. So now that we have the big picture of all of the basins themselves, I wanted to step you through what we had for those 7 quantitative basins. So each one of them have their own unique parameters. The St. Lawrence Lowlands contains prospective CO2 storage in deep saline aquifers. Despite exploration since the 1950s, no significant hydrocarbon discoveries or suitable depleted reservoirs exist. So available subsurface data helped us characterize this potential. And what we see here is that we've got a reservoir seal with the Cambrian Plastam group, sandstones, and then a seal that is regionally extensive Ordovician carbonates and overlying shales and siltstones of the Utica, Sante, Rosalie, and Lorraine. There are many key uncertainties that still remain around lateral continuity and vertical connectivity, especially in structurally complex areas that need to be taken into consideration. Next, we'll move into the Moncton Basin. The Moncton Basin is Carboniferous-aged Maritimes basin in southern New Brunswick. It comprises 5 key subbasins. Collectively, we're going to refer to them as the Moncton Basin. These subbasins have potential for long-term CO2 storage in saline aquifers. There have been extensive historical exploration for natural gas, salt, gypsum, potash, and this provides a fantastic subsurface data set, including wells and seismic data, to support our regional evaluation. While some hydrocarbon production exists, While some hydrocarbon production exists, examples are the Stony Creek and the McCully fields, no suitable depleted reservoirs for large-scale CO2 storage have been identified. Promising storage complex has been identified in the Central Basin, featuring the sandstone units of the Horton Group, locally the Sussex Group, and the regional extensive wind group as the seal that you can see here. One of the things that you're going to note as well as we step through these basins and that traffic light system is in some cases we have good indications of lithology and depth and sand thickness, but permeability tends to be one of those areas that we need more data and more information. And there's a bigger question mark in terms of what you're going to get. So something to keep note of as we step through. Next, we move to the Magdalen Basin. The Magdalen Basin has 3 different storage complexes. We saw some maps displayed earlier in the presentation that went through this. The basin is relatively underexplored with limited well and 2D seismic data, so it can lead to higher uncertainty in the reservoir and seal characterization. But within those 3 storage complexes, we have the Upper Carboniferous, which is the Cablehead, the Burdell formations, as well as the Lower Carboniferous Horton Group. Again, we're going to have some uncertainties that relate to the reservoir quality due to the data availability and the seal integrity and lateral continuity. Next, we move into the onshore Windsor Basin. So this basin shows that we have some potential in the sandstone units of the Horton Group, as well as the carbonate evaporate strata of the Windsor Group here. Historical exploration has been in salt, gypsum, potash, and base metals, so this provides some subsurface insight, but hydrocarbon exploration has yielded no significant discoveries to date. There are some limitations due to limited well control and understanding in terms of that lateral continuity for your seal. Supporting analysis includes depth and net sand mapping, cross-sections, and evaluation of the reservoir and fluid properties to assess the storage suitability. Again, there are a lot of parameters here. We have a lower overall storage number, and we need to understand a little bit more about the permeability. Next, we move into the South Whale and Whale Basin. This basin is underexplored. It has limited well and 2D seismic data. And so there is a significant amount of uncertainty in reservoir and seal characterization and continuity. We do have 2 potential storage complexes that have been identified, the Lower Cretaceous Mississauga Formation and the Eider member or the Logan Canyon Formation that you can see delineated on the strat section here. These complexes may support CO2 storage in a supercritical state. Additional considerations include limited well control and restricted marine areas, which may impact future development. Next, we move into the Jeanne d'Arc Basin. This is another heavy hitter in terms of having a lot of the green light parameters, some question marks in terms of the thickness itself, but it has prolifically been explored with both saline aquifers and producing hydrocarbon fields, offering strong CO2 storage potential. We've got a great data set to support that evaluation, both in well control and 2 and 3D seismic. So there is a unique opportunity in this basin for CO2 storage in depleted fields at the end of field life, in addition to saline aquifers. The reservoir quality is strongest in the South Central Basin and declines northward due to depth, facies changes, and overpressure. So we have 5 key storage complexes that were assessed quantitatively here. And this is all delineated again on the strat section: the Lower Cretaceous, Hibernia, Ben Nevis, Eastern Shoals, Upper Cretaceous, Outer Bay, Fox Harbor, and the Lower Tertiary being the South Mara. Additional intervals, the Catalina and the Jeanne d'Arc formations, were evaluated qualitatively for note, but there's a lot of additional information that can be found in the Atlas chapters. Next, we're going to move into the Scotian Basin. So we've got a basin that is showing that you have some of the highest storage potential of all of the basins that were quantitatively analyzed. So there is a wealth of information, not only from seismic, but wells and cores. The exploration maturity within this basin itself has provided a lot of data to go through and do the characterization. We have 4 primary plus 1 combined storage complex that have been identified. That's the Cretaceous Logan Canyon Mississauga formations, the Jurassic Micmac formation, and the Abenaki Reef complex. And in some areas, the seal continuity is uncertain, and it leads to combined storage complex with the Mississauga, Micmac, and Logan Canyon with distinct reservoir characteristics. Now, John's going to get into a lot more of the information about the geometry of these units and how they all fit together. But what that does at this point is give you a basis of understanding of all of the results that we have seen from a quantitative standpoint. So now I'll hand it over to my colleague, John.
Thanks, Christa. Make sure I've got control here. There we go. That's a nice thing. And that's working. Great. Well, thank you for that quite thorough review of everything, and you summarized the entire basin. So I guess my job is just basically to walk everyone through what we did on in the more detailed view on the Scotian Basin. As I said, our task was to assess the geological storage potential and develop an inventory of where is the best area within that basins and which is the best portion of the geology in which to potentially store CO2. So with that, we need to then review data that is available. So we're data takers. We're not really data makers. We're not going out and acquiring seismic or drilling wells. We have to take those data in and synthesize it as much as possible. And really for the Scotian Basin, there's a wealth of data that's available. Much of it was expertly curated by a variety of different sources, specifically a number of petroleum fairway analysis. So that data is equally used for evaluating petroleum potential, but also for evaluating the potential of CO2 storage. I'll talk about the basin overview, the geological setting and evolution, and then walk you through how we did the analysis for the different potential storage complexes. The inset map here is just once again the situation of where these basins are. The Scotian sits in the North Atlantic, just offshore from Nova Scotia. It's a relatively large basin. And we also show on here some of the major continental scale fault systems. These fault systems were generated during the coalescing of the Pangea, the supercontinent Pangea, back in the Paleozoic, and then were subsequently reactivated into forming basin bounding faults when Pangea subsequently broke up in the Triassic to the Jurassic. And I'll talk about that in a little bit more detail when we go into the basin architecture. So again, the data that we're looking at, we've got it's a relatively large basin. There's a large amount of seismic that is available, that was available for the petroleum fairway analysis, and Mark Deptuck and others to do their magic in terms of the systematic mapping in the area. There's a lot of wells. There's a lot of wells with core. There's a good amount of wells in which we had digital well logs, both raw LES curves and interpreted lithologic wells, and then wells with pressure and temperature. So the makings of this is we've got an awful lot of data to go through and do our evaluation. But we should note in here the data specifically in the well control. It's quite clustered. We've got two areas of focus for where those wells were drilled. They were drilled because of the petroleum potential and the follow-up gas development. But when we move away from those, the petroleum industry didn't do a very good job in terms of adequately delineating all aquifers. They were looking for targeted structural closures. So we don't have as much data in the in areas away from active where there's well successes. And in that, as I mentioned, we've got of the wells of the surfaces that were mapped in with this regional seismic. We've got a number of regional surfaces. These are primarily on key seismic markers. The Cretaceous 101, the Cretaceous 94, etc. But those had to be then adjusted using the well control to fit to where the main surfaces, the main bounding surfaces, basically the top and base of the compartments and the seals. So there's a matter of fitting and doing some juxtaposing of those map surfaces to the well control, and it's sometimes it's not. Sometimes it's quite easy. Sometimes it takes a little bit of monkeying around. So the Scotian Basin is not simply one basin. It's comprised of a multiple individual subbasins, and we show here that you've got individual subbasins like the Abenaki and the Table Subbasin, and they're often separated by ridges or fault scarps. And then we also see another basin just to the north. It is a little bit of an outlier, and it's the Orpheus Basin. It's got a different orientation, and as we'll talk about, some different stratigraphy. Now, these basins were formed because of the complex relationship on how rifting from Pangaea happened. The inset map here is a paleogeographic map uh, showing an artist's interpretation of what Pangaea was like at the onset of rifting. So North America, or will be North America, is situated here. North Africa sits here. And then this is the point in which, about 185 million years ago, in which there was an onset of rifting, and we actually had a little bit of an isolated seaway developed. Those as I mentioned, there's these major faults that were developed that formed when Pangaea was developed. They were reactivated when Pangaea started to split off, and that's shown in here. So we had a number of individual fault segments at a variety of different orientations. Some of them orthogonal to the motion of rifting. Some of them somewhat oblique to that. And what happened was when the rifting started, we had the orientation of extension was sort of higgledy-piggledy across the basin, and we developed these small individual subbasins. Eventually, as the rifting commenced further, they started to link up, and the basin talked to each other, and it formed one large basin. So we have individual basins that have got different characteristics of them, and then eventually they talked. There was an overall one super basin and that's the Scotian Basin. And here's a cross section and a stratigraphic chart that really describes the sediments within this basin, and it's following an idealized classical rift basin sequence. We've got with the onset of rifting in the Triassic, you've got a relatively thick amount of continental red beds, the Eurydice formation, and that's red beds and sandstones. And then that is subsequently overlain by by salt deposits, the Argo salt. Now, the Argo salt was relatively, some basins had more of it, depends on which basins were actually being rifted open in the Triassic. We see in the cross section that the salt occurs in the basal portion of the rift sequence, but also can potentially climb, and that's from salt diapirs or movements associated with faulting. That sets up a fairly complex situation, but we're more looking at what's happening in the shallow water reaches. So and the salt movement, the more complicated salt movement occurs into the deeper water, is often in the deeper water regions. So the Argo salt is then subsequently overlain by Jurassic sequence, mainly of carbonate dominated. We see the thick Abenaki reefal carbonates. Associated with that on the flanks of the Abenaki is the Micmac deltaic complex, and we see that here. The Micmac is aerially restricted to smaller subbasins, and that was because the basins weren't necessarily talking to each other to the same extent as they were later on. In the Cretaceous, but then we start seeing thick deltaic complexes coming in. The Lower Cretaceous Mississauga, and then the Middle Cretaceous Logan Canyon. And you see that in the cross section. You've got the relatively thick section of the Mississauga that it comes is thinner in the proximal reaches in the towards shore, thickening as it's going into the deeper water. And then we note that the whole sequence continues into the deep water, but there is a regional shelf break that separates the sandy area from the shaly area. So we net out the sand, and the sand is more restricted in terms of the shallow waters. And that's also happening with the Logan Canyon. We see a relative thick delta deposits prograding out onto the slope, and then that has been subsequently overlain by a top regional seal, both of the Petrel and the Dawson Canyon. So it really sets up that we've got a number of very good candidates for CO2 compartmentalization, reservoir, and seal pairs. It really is shown here. This is a stratigraphic cross section. It's going from the shallow waters towards the Orpheus Graben and then going out towards the deep water. So shallow water on the left-hand side, deeper water on the right-hand side. It's a stratigraphic cross section that's hung on a marker, and that allows us to see how the different reservoir compartments relate to each other. And we're utilizing the interpreted lithological logs, and that shows yellow is sand, gray is shale, and we also see areas of limestone. So with that, you get a very quick visual of the lithology and seal potential that can be mapped across the basin. We show here the lower Jurassic Micmac complex related into the reaches, and it doesn't extend into the deeper water. Again, the Mississauga thickening from the shallow water and the more proximal reaches into the deeper water, more distal reaches. Now, one thing to be noted is that the Mississauga continues. It will continue down in this part of the section, but we've truncated it. We know that there's a top of overpressure, and that's a regional overpressure. It's a depth and lithology dependent phenomena. And what we've chosen is to truncate the Mississauga, mainly the Mississauga storage compartment by the top overpressures. If you have too high overpressures, you have a potential. It really makes it more difficult to store CO2. You add more CO2 in an overpressured compartment, and you have a potential of fracturing or losing containment. The Mississauga is overlain by a regional shale, the Caspi shale, that can be mapped in deeper water quite readily. But as you're going to the more proximal, you lose that ability to continue to map across. So we think that in this area, there's a combined storage compartment of the Mississauga into the overlying Logan Canyon. Logan Canyon, very similar to the Mississauga, is sand dominated in the proximal reaches, and becomes a little bit more shale dominant as you're going into the more distal reaches. But the entire area is overlain by a good top super seal. So really, these have the makings of a tremendous storage conditions. We've got excellent quality reservoirs, stack potential, and they can be mapped quite readily. This is the cross section that goes along the basin in more of a west to east orientation, going from down further into the western portion up into the eastern portion, and the west is on the left-hand side, east is on the right-hand side. And what we're showing in this is, again, we're showing the same the interpreted lithologs, but in this case we see a thick Jurassic carbonate sequence, the Abenaki carbonates, which were the reservoirs for the deep Panuke. And they map out along the southern margin of the basin. So you see thick carbonates in here, and they're juxtaposed or away from the Micmac deltaic deposits. And again, we see a regional variation in the net to gross. In the center portion of the basin, we have the highest amount of sand that can be that's deposited, and as we're going laterally away from that, into the southern portion of the basin, the net to gross decreases, so that we've got more shale. And we'll show that's a matter of interpreting that and mapping that across the basin to constrain our net reservoir. Sum total is we've got excellent quality seals, they're excellent quality reservoirs, good quality seals that can be mapped across much of the basin, and that forms the Micmac storage compartment, the Abenaki storage compartment, the Mississauga storage compartment, and Logan Canyon. And where those the intermediate top seals are absent, they combine into one complex. But there is regional seals that can be mapped across the basin above the Logan Canyon. I mentioned the Orpheus Basin. The Orpheus is a little bit of an outlier. It's actually more proximal. It's actually closer inland than the Goshen Basin, but it's got quite different sediment fill. We see a thick amount of salt. We see the eurydice that has been found in one well. But what we don't see is the cast of characters that we mapped in the Scotian Basin to the same extent. There is the Dawson Canyon and Petrel, but we can't map that across the basin. So there is a few wells in which that top seal is absent. And then we do see the Mississauga storage compartment and then the Caspi shale that can be mapped in a couple of wells, but not in all wells. So the upper portion of it, the shallower, the Jurassic and the Cretaceous storage compartments, are somewhat more complicated, and we don't see them to the full extent as we see in the Scotian Basin. But what we do recognize is there's potential of the thick Argo and the Eurydice. And this is similar to what was mapped in the Fundy Basin. So for the Orpheus Graben, we consider that more of a qualitative basin, but we recognize that there is potential, just not the well control necessary to really quantify it. So now, how did we get at those final maps of the total CO2 storage potential? We ended up going through mapping and calculations. So for the pore volume, we need to understand the distribution of the seal and truncate that in areas that are greater than 800 meters. We need to understand the net reservoir, and that's using map surfaces, translate those into isopac maps and the key storage intervals, and then integrate well logs and core data, and then to come up with the net to gross and porosity. And that really gives us, in terms of the bulk volume that we're dealing with. And I'll walk you through what we've got. These are the depth maps. These are depth to the aquifer midpoint for the Logan Canyon, Mississauga, Micmac, and the Abenaki. You note that in here in the Logan Canyon, we actually had to truncate it to areas at 800 meters. It does continue further shallower, but in those reaches, CO2 would not be super critical. And I mentioned that in the Mississauga, we actually truncated the more distal portions of it. There's an area of potential that occurs off board, but that would be into the area of overpressure. So and we truncated that. So we've reduced our area somewhat, and these are the areas of concern that we do for our isopac mapping as well. And so for isopac, we generated an isopac mapping, and that's the thickness of the interval. And then we have to come up with the net stand or net carbonate maps, and that really is taking a gross isopac multiplied by net to gross. So we mentioned that using well control, we can identify the variability in net to gross both proximally and distally in a dip direction. And it's also along strike. And so we integrate that, and we map that in this basin for the Logan Canyon, the Mississauga, and the Micmac. I actually end up mapping those by hand. The Abenaki was done in a separate sort of way because carbonates are kind of tricky rocks. So this is the net reservoir that we're working with. Now, to populate that with the amount of porosity, we, instead of going to the well logs, other basins we had to bias it towards the well log measurements. But this basin, we've got a wealth of data. We've got an awful lot of core data that is both geographically spread out as well as core data spanning a lot of depths. So for the Logan Canyon, Mississauga, and Micmac, we used core data. We took the core data, we binned it, came up with sort of average numbers on those bins. And then from those bins, those are the ones we fitted a best fit curve to. And so that is our predicted porosity trends is on the basis of those data. Now you note that that the bin numbers and the final predicted porosity trend, they don't really capture all the ranges of the data set. And that is a function of doing this on a basin scale. If you're doing it into more to a more prospect-oriented CO2 storage area, you need to reintegrate some of the variability. But for the scale of which we're working at, we did an average and came up with this porosity depth trend. Now, I mentioned that the carbonates are a little bit different. I refer to plastics and sands as being the sort of the logical rocks because they form from gravity processes. But carbonates are a little bit the illogical rocks. They're formed by organisms and responding to water depth and light, and so they're a little bit more tricky. So for porosity in the carbonates, we didn't use the systematic variability with depth. What we did is we used the mapped facies relationships and there's a number of different maps that were generated for the Abenaki reef trend. And then we applied a facies by facies porosity transform to generate the net porosity map. So that's something that was templated. That's the same relationship that we developed that we use here that was developed in the British Columbia Atlas. So we're being consistent across areas that we've evaluated. So next is looking at the permeability. We recognize that permeability is a very important rock parameter because it really is a function of how fluids flow. It's a measurement in oil and gas, so it's how much fluid can be drawn from it, what's the rate at which can be drawn. And we can turn that around in terms of CO2 evaluation on how much can be injected and what's the rate of that. So we see that both the Logan Canyon, Mississauga, and the Micmac, there's a relatively good, strong relationship that can be evaluated. And we have done a best fit curve through these data. And this shows the relationship of the sandstones, the clastic reservoirs. They behave predictably. What's different is the Abenaki. The Abenaki has a highly variable porosity permeability relationship. Pardon me, I'm just going to drink here. And that, so for instance, a 20% porosity in the Logan Canyon ends up with about 10 millidarcies. 20% porosity in the Mississauga, the clouded data, around 10 millidarcies. You don't even get to 20 millidarcies, 20% porosity in the core data from the Abenaki, but we see values in 10% porosity of up to 10 darcies potentially. So and we know that highly variable porosity permeability relationship challenged the Panuke gas recovery, and we recognize that there's potential that may have posed some challenges for CO2 injection. So I've walked you through what we've done in terms of our coming up with pore volumes on a basin scale. Now we need to understand the pressure and temperature, the physical parameters, the pressure and temperature, so that we can understand how the CO2, the physical nature of the CO2. So from that, we're biasing it towards the well log information for temperature. On each one of the well runs, there'll be a temperature that is measured. You have to correct for that for borehole conditions, but you can come up with an average temperature. That in this case, it comes out with an average of about 28, 29 degrees per kilometer. But we also recognize that there's some areas which is higher and some areas which are lower. So we actually mapped out the geothermal gradients across the basin and applied those to our calculations. For pressures, there's a wealth of pressures, both from wireline data, from NCP, also from production tests and drill stem tests. So we've got an awful lot of pressures that were acquired in the basin. And we see much of this falls along a relatively normal pressured gradient. We recognize that as you start to get into depths below about 3,500 meters, there's potential for overpressures. And as I mentioned, we've tried to cleave these out and not include those in our analysis. So we have now on a basin scale, we have all that we need to come up with for our total for storage potential. We've got pore volume, we've got CO2, density considerations with pressure and temperature, but we recognize that we are doing a relatively deterministic calculation on both pore volumes and the partial pressure of CO2. But we recognize that there's going to be a lot of variability in that. And so we capture that variability in that EC line storage efficiency factor. So we've got a tenfold range in storage efficiency from 0.05% to greater than 5%. You can quibble on the numbers. I think that what we've done is we've been consistent in terms of our evaluation. E saline is a number which I think that the more work in different areas, we'll be able to arrive at more rigorous estimates in terms of what saline to use, but we've chosen to use a broad consideration on this to come up with a broad range of values. And that really, for the Scotian basin, it ranges from a high number of 410 metric tons to a lower number, a P90 number of about 38. So again, over a tenfold range in total estimate. But the number we report and the number that is mapped out is really the midpoint at 152 total metric tons, and that's really relatively evenly split between the Logan Canyon, Mississauga, and lesser amounts in the Micmac and the Abenaki. So that's the aquifer storage potential. But in the Scotian, it was, oh, I forgot, this is the, of that storage, we see that, Logan Canyon clicks green on all parameters. We've got a top seal across the basin. We've got excellent quality sands. The only thing that really comes out is a little bit more yellow is the top seal considerations on the Mississauga and the Micmac. But again, since we have the top seal for Logan Canyon, we really have a super seal across the basin. So as I mentioned, the reservoir, so we've got the total calculated for the aquifers, but what we haven't done is looked at the depleted pools. So the the production in the oil and gas started in the Panukan Coset with gas or with oil development back in the early 90s. That then was we transitioned to a lot of gas production, both in the Sable Island and then the Deep Panuke. And then the whole the basin was basically the two later developments were abandoned and decommissioned in 2018 and decommissioned in 2000. So we've got an estimate in terms of the amount of fluids which were produced at that time, and from that you can end up with we can calculate the amount of CO2 that can be re-injected or stored back in those same pools. And we roll that back up into this. We have the deep saline aquifer storage potential and the depleted pools storage potential. And you note here about 124 metric tons potential in the depleted pools is minor in respect to the total amount of storage potential in the deep saline aquifers. And we note in here that of those deep saline aquifers, you've got main sweet spot and the thickest and richest sand deposits in here and in here, and then they decrease laterally away from that. So that's the Scotian Basin. That's what we've our calculations. That's how we got to them. We recognize that there's potential technical risks. Some relate to data coverage and the clustering of things. Other data relate to the reservoir quality and risks. Really, and for this, the most important is the permeability, but we don't see a significant risk on that. The only pause for concern may be the Abenaki carbonates. How did they behave putting CO2 back in? And then we do recognize that there's a potential for induced seismicity anytime you're injecting fluids, but we don't recognize that as being a significant risk in this basin. So for this, again, in conclusion, we've got each basin was evaluated in a similar nature to what I walked you through for the Scotian. We've got 7 basins which were done on a quantitative characterization, another 8 basins done on a qualitative characterization. And we've got a sum total on what these basins look like in the inset table. And from that, I will transition back to Christa.
Awesome. Thanks, John. So thanks for bearing with us, everybody. I know we're about 1 minute over, but a lot of information to get through. I'm sure it's felt a little bit like drinking from a fire hose, so appreciate that. But just to conclude this, These are the 7 basins that John had referenced in terms of that quantitative analysis. These models, again, are effective for regional scale predictions, so they represent average conditions. They may miss local heterogeneities, meaning variations that you're going to need to consider on a site-by-site characterization. And in the converse to that, you have lower ranked zones that may be showing up in those yellow or red areas that could have higher porosity or permeability pockets that can exist. So they should be verified with observed data as well. We've got basins that offer stacked storage potential, like the Jeanne d'Arc and the Scotian. So we have a much higher storage potential within those areas themselves, and then other basins that may only have one storage complex. But the P50 storage resource has been accounted for all of those basins. Again, the offshore basins like the Scotian, South Whale, and Jeanne d'Arc are notable for their thick, high-quality saline aquifers with strong storage potential, and our onshore basins, such as the St. Lawrence Lowlands, the Moncton, and the Windsor, have a lower overall potential, but still may support smaller localized CO2 storage projects. So with that, we wanted to conclude that CCS is a crucial technology whose rapid deployment at large scale is really going to help the world meet its global climate goals. Geological storage of CO2 occurs naturally. Industry has been storing CO2 deep underground for the decades, so it is something that we know very well and can help minimize some of the risks that are associated with it. The first step in developing any CCS project is really understanding the subsurface. And I think, what you saw today was a high degree of variability, and understanding all of the different components in that is essential to know what your storage resource is going to look like. And this study really has helped create an inventory of the most promising geological storage options for CO2 in Quebec and Atlantic Canada. We've estimated the CO2 storage potential and highlighted areas of potential risk or uncertainty. And this is really to help support exploration and development plans, as well as to enable industry, governments, Indigenous groups, communities, and others to make these informed decisions. Now, our study is now live, so we encourage you to please go on to the site. We're going to be sharing that in the chat shortly, and appreciate you hanging in there with us to the end of this presentation. Part 2 is coming up next week, and that's CO2 storage and full CCS value chain, so cost modeling, so taking this, to the next step from the geological characterization components. And thank you again. John and I will hang out for about 5 minutes. For those that have any questions that they would like us to answer, you can also feel free to type them into the chat, and we can follow up with you after, or look to address them with you at a later date. So thanks again, everybody, for joining us today.